Okay, today what we are going to do is we are going to learn about registers. Okay, now how is the registers different from the uh, from the flip-flops? Okay, so let's see. A register is a group of binary storage cells suitable for holding binary information. Right, what does it mean is, like in a flip-flop till now we were we were trying to store a single bit information. In register it is multiple bits, like it could be like 8-bit data, it could be 16-bit, it could be 32-bit, it could be 6. Like now you have 64-bit processors, right? Most of our we are using either 32 or 64, right? So if you see, okay, can somebody say, you might have noticed, if you have an 32 bit processor, right, if you see your system requirements, it would say 86 series or something like that, whereas for 64 it would say just 64. For 32 it is not written 32. Anybody, have you ever thought of it? Yeah, in for 32-bit it's written into, yeah, exactly, right? Like we had that 86 processor, which was one of the most successful processors those days. Subsequently Intel from 86 they graduated to Pentium, then Pentium 1, 2, 3, 4, and now you have dual core and all. So till all these microprocessors had the same instruction set of 86. It was very powerful, which you will study in your next semester MPI. And if I will request not to give me such huge course, and I have drained out completely. But then if they give me microprocessors, then I'll be teaching you microprocessors also. I have handled that course once, so I'm slightly comfortable with that. So so in that case we'll learn about 88. So 64-bit processor onwards, it's a totally different instruction set. So that is why it is known as 64. It is not written even for 32, it is written x86. Okay, because the instruction set of 86 is followed till 32-bit processors. From 64-bit processors onwards, a new instruction set has been generated. So that is the reason for it. Okay, now coming back to our topic. Okay, now it says ki register is nothing but which can store n bit of registers, and it will have obviously for the number of if it's an 8-bit, it will have 8 flip-flops, and if it is a 16-bit register, it will have 16 flip-flops, and so on and so forth. In addition to flip-flops, right, registers may have combinational gates that to perform certain data processing tasks. This is very, very important. It is not just the flip-flops, but also a register will have inside. A register is a combination of flip-flops and few combinational gates, and these combinational gates will perform certain data processing tasks. That is, like how to put the data into these registers, whether it to be put serially, it is to be put parallelly, or you need to reset it. So all those functions also is taken care of by the internal circuitry of the register. So the register has gotten flip-flops as well as some combinational gates. Okay, so we'll see that and how that is done. Okay, so this is one of the simplest parallel transfer data, where clock is given. So whenever the clock is given, I1, I2, I3, I4, so that will get stored into this register. So you have A1, A2, A3 as the output. Okay, so what is the drawback of this circuit? Anybody?
So they share the same clock.
No, that is a good thing. Sharing a same clock is good thing, because it is synchronous. Okay, they won't have any problem. But it, yeah, like you said, it is something related to with the clock.
So will there be a time delay because of The arrangement of the D flip-flops.
Yeah, no, I mean, okay, I'll just give a hint. Probably it's too early to ask you that question. The thing is, like in this, what happens with every clock, the data would keep changing depending on input. But our requirement of register is, see, I have some data, I've stored it in a register, and I want to access it when I want it. Not that very next clock, in the very next clock, I might do some other operation not related to this register. Okay, I have taken, say, I have fetched from my memory some data, put it into one register. In the next clock, I'll go and take some other data and put it into some other register. In the third clock cycle, I would want to add these two datas in these registers and give me output. So these registers can't be given clock, the central clock, okay, because with every clock the data will keep changing. So I have to change the clock, and I'll have to have an enable pin. It will be clear in the next diagram. So if you see, it is I0, I1. Okay, here also it won't be clear. Here what we have done is we have given one more clear signal here. Okay, so whenever we give clear, all the inputs will be cleared out here, right? So this also will have the similar problem of whenever there is a clock, input and output will get the output will ask for an input and it will accordingly get slaved. So that is not an ideal situation. Okay, this is what an ideal 4-bit register should look like. Now if you see here, okay, this is the clear signal, the last one which is there in the bottom. Okay, can you see my mouse? Should I increase the size?
It is visible, sir.
It's visible. Okay, so clear is 0. Okay, when the clear is 0 here, it will be 1 here. So this is bar. So all these will be enabled. Okay, and if clear becomes 1, it will be 0. All these will be set to 0. Now what is the next thing? You see, the clock. The clock is given to each one of these flip-flops. Okay, each one of these flip-flops. But what is happening to the load? If load is 0, what happens? You see, this AND gate is 0, right? All these AND gates will be 0 when load is 0. So what happens? All the set and reset pins will be 0. Okay, so what happens if this is 0? Whatever was the previous state, it will continue to hold that data, right, as long as your load signal is there. So whenever you want to load any data to the register, you will give the load signal high. Okay, that will enable all these AND gates. So it is set and reset. Each signal has got an inverter, so it will set and reset. So accordingly the data will get stored here using the load command, right? So and then after that, that load is removed. So this data is permanently stored here. So using the load signal, we can at any whenever we required, we can store the data here, and we can then put it low, so that data will remain there as long as you give the next load signal. Is it okay with everybody? These are very, very basic things which we need to understand properly. I can repeat it in case.
Sir, could you please repeat that once?
Yeah, okay. See, whenever there is a whenever the load signal is 0, okay, this is a buffer. If you see, there is no inverter here. So all the AND gates will be, output of the AND gates will be 0, right? Is it okay?
Yes, sir.
Okay, if it is 0, set and reset both are 0. So what would happen to this register?
There would be no change in the data.
Okay, whatever is the data. So whenever I want to pump in some data into this register, I will give load equal to 1. So all these AND gates will be enabled now, right? Okay, then depending on your input, I1, I2, I3, I4, whatever I give. Suppose I give 0, 1, 0, 1. Okay, and load I give 1. So when the clock comes, this will be loaded as 0, 1, 0, 1. Whatever is value of I1, I2, I3, I4 will come as A1, A2, A3, A4, and then I put the load signal low. Is it okay?
Yes, sir, understood, sir.
Right?
Thank you.
So thus this becomes a storage unit. You will store the a 4-bit data as long as you want. Okay, there is no time limit. As long as the power supply is there, that data will be available. As long as there is a power supply to these ICs, that data will be available here. You can rewrite the data using a load signal. So every clock signal, it will not, this data will not change. Even if I1, I2 changes, right? So you can have multiple registers, and in the next cycle, this I1, I2 data can be written into the next, like if suppose I1, I2, I3, I4 is the lines which is connecting the memory with your CPU. Okay, in one cycle, this register will be enabled. So whatever data is coming from the memory will be written into this register. In the next cycle, I'll put this load 0 and the load high for the next register. So whatever data is coming from the memory will be written into the second register. In the third cycle, I might want to add these two datas. Okay, is it okay how the system works?
Yes, sir. Clear, sir.
Okay, all of you. Okay. So you can stop me if it's not clear. Okay, no problem with that. Okay. Okay, this is another schematic where instead of SR, it is being implemented with D flip-flop. Okay, so let's go with the clear signal. First of all, if the clear is high, you will find that, okay, all the if the clear goes low, right, so all the reset will be activated and it will all go to 0. So the clear has to be normally high so that the reset is disabled. Okay, so that is it. Clock is again given to all the flip-flops. Okay, so clock is always, we never try to give clock through any gates, okay, because that will cause jitter. If the clock is not reaching in an IC spread on in all the flip-flops, it will cause any delay in the clock, okay, will generally cause jitter, and it adversely affects your performance. So in an IC, generally you will find one clock tree which is running throughout the IC in between different blocks, so that the clock is smoothly distributed. So clock, we never do any chedkani with the clocks. Okay, so the clock is generally given directly. Now with the data, coming with the data, if you see, if the load signal is data changes with each clock. Now let's see what happens. Okay, if the load is 0, it is 1 out here, right? It is 1 out here and it is 0 here, right? So this 0, if you see, is with the AND gates which are coming from the data lines. Okay, this output of the second inverter is connected to AND gates. Output of the second inverter from the load line is connected to AND gates which have the other inputs as D0. So obviously, if load is 0, then all the data lines and AND gate outputs will be 0. So we rule out that. Then what happens then? Something has to be given to D, right? What is given in D? The Q is taken from here and given through a AND gate, and that is load bar. That means whenever the load signal is 0, through this AND gate, the previous data is again fed back here. So it will retain the data here. Is this much clear to all of you? I can, okay, and whenever the load signal is high, you will have a 0 here. So this 0 will disable all this feedback path which is coming from the Q, and instead enable the AND gate which is below the AND gate, which is the not from the top, the bottom AND gates here, 1, 2, 3, 4. And what are those bottom AND gates? They are the data which is coming from the left hand side. So that data will be fed into these registers. So this is how, using an load signal, we can give whatever data we require to be fed in can be fed in using the load signal. And when the load signal is not there, when it is low, you will form an feedback from Q0 itself. So the same data will be available in these circles. Okay, sir, is this the rectified version of the initial register implemented using D flip-flops? No, the last circuit was using SR flip-flops. Okay, This is using the D flip-flop. One before this one, yeah, this is this was with the D flip-flop, right? So this is now modified one. Okay, yeah, correct. So this is with the modified circuit. Now coming to shift registers. In shift registers, you give a serial input, serial output. So you give a serial input here. With each clock, the data will move from here to here, here to here, here to here, right? So if you have an data which is coming serially, like when you do we are doing USB transfer, right? So we are doing serial, the data is coming serial, right? If it is a 64-bit processor, you don't have 64 lines going from your pen drive to your CPU, right? You can't have like that, right? So 64-bit data is to be stored into your, say, USB drive, your pen drive. So you will send the data serially. So you can put the serial data here 64 bits, and when the data comes, you can read parallelly from those. So this is the application of serial in, serial output shift registers. Is it okay, the application part? Where do we use these shift register? Anyone? Shall I move ahead? Can somebody respond?
Sir,
Yeah.
excuse me, sir.
Yeah, tell me.
Sir, so these basically act like a buffer for the bus, as in like where you connect your USB to the bus. So these keep on taking bits from your data that you are inputting and storing them, and then giving them to the processor or wherever that has to be transported to.
See, there is a serial data which is coming, so you will have to put an serial say if it is a 16-bit processor, you will put 16 registers. So the serial data will come once that 16-bit information is available. Okay, then that 16-bit data within the processor, you will have 16-bit bus line, right? So that data will be transferred onto that bus line, correct? Okay, again then
Yes,
you will fetch 16 serial data. Similarly, when you have to give out data also, you will feed all the 16 into one register, and you will take serially out. Is it okay?
Yes, sir, understood, sir.
Yeah. Agarwal, could you understand? Yeah, okay, so let's move forward. Okay, now this is an universal shift register. Okay, so you need to understand this very carefully. This is very widely used. Okay, so we will see what is done. Okay, this is the serial input for shift right. This is the serial input for shift left, right? These are the parallel inputs 1 2 3 4. These are the outputs which are available 1 2 3 4. This is the clock which is given to all the 4. This is the clear signals. Okay, so clear, though we don't have to discuss, we all know what it is. Clock also is given to all the 4 inputs. Now this is a 4 into 1 mux. Okay, so the control signals for all these 4 mux is the same, S1 S2. Okay, now let us take case by case. If I give 0 0, right, to all these 4 mux, the control signals are given 0 0. So what would happen? So 0 means it will take in all these 0 lines will be activated, right? So what is the input to this mux? This is mux. Here it is coming from Q3, here it is coming from A2, here it is A1, and here it is A0, right? So A3 is again available as output. So what happens when the clock comes? Can anybody say? If
So data is retained.
pardon?
So is data retained?
Yeah, it is, data will be retained. You are giving S10, S20. When the clock comes, the same data will be retained here. Okay, so let's take the second case. Second case will be, okay, 0 1 0 1, so that this 1 is going to be activated here. So what happens, let's take on a flip-flop wise, what happens, this serial data is coming here, 1 here, right? So what happens, 1 is available here. So with the clock, okay, the serial input for write shift, okay, this data will get into this flip-flop. Is this clear to all of you? We'll see what happens to the next register. Okay, when it is 0 1, whatever is the serial input will come here. Anybody can just say yes or no?
Yes, sir.
Yes, sir.
Okay, yeah, this shifts the data to the right flip-flop. Yeah, we will come to that. Now this data has come here. Yeah, so what about this one? 1, where is the 1 connected here? 1 is connected from here, it is connected to A3. So A3 will come here, so the data of A3 will come here now, right? So with the clock, the data of A3 will come here. This data input has come here, it will A3 will come to, data will come to A2. And what about this 1? If you see, it's coming from A2, so A2 will come here. A1, if you see 1, it is coming from here, A1. So A1, it will come at A1, right? So what happens is, all the data is shifted towards the right, and one new data is taken from here, from this. Is it okay? Like Vishwas said, it's going to shift the data to the right. So this is known as serial input for shift right. So it will keep shifting the data towards the right. Is this clear to all of you?
So,
Yes.
Yeah, tell me.
so like whatever input we give to A3, like the same input will go to the second mux, or the previous A3 will be going to second mux.
No, I didn't get your question. Could you just repeat?
So if A3 was 0 initially, then we give serial input as 1. So A3 will be changing, right?
Yeah, A3 will be changing. No. See, with every when the clock is going high, okay, whatever was the data previously held will be taken. It will never take the new data for any edge triggered devices. Okay, in exam also probably one or questions was framed. Answer key might be wrong. I'll have a look at it. Whenever there is an edge of the clock, it is not the new data which it will capture, because there will be some propagation delay. Right, definite propagation delay will be there, and also there is something known as setup time. So you have to give a data slightly before the clock comes for any flip-flop to work properly. So we'll see those fundamentals towards the end of the class, because I'll have to get at the transistor level to explain you those things. So always remember, during the rising edge of the clock, whatever data was previously held at that D input, that will be captured. Okay, is it okay now?
Yes, sir.
Okay, so that okay. Now take an input combination of 1 0. 1 0 is 2, right? So what happens in this register? 2, it is coming from the A2. For here 2 is coming from A1. For here 2 is coming from A0, and for this 2 is coming from the serial input for left shift. So it is going to shift the entire data towards the left, taking a new input from the serial input for left. Is it okay, this much? All of you?
Yes, sir.
Okay, now let's take the fourth combination. Can anybody tell what is going to happen for 1 1? S1 S2 1 1. Yeah, for 1 1 the parallel
So will it take the data from the processor where it's like getting 4 parallel inputs and just dump it in the registers?
Correct. This is the parallel inputs, right? So this is how we convert a parallel to serial data converter. You can use this, right? You have, suppose you have an data coming from the CPU. You can dump that data into these registers, okay, and then using S1 and S2, and then subsequently make it in a serial out, and then you can take it from the you can use this, like if you keep after dumping the data, right, if you enable serial input for shift right here, whatever happens here, for the next 8 cycles it will give you the serial output here. Will it give the serial output here at this pin? No, sorry, that won't happen. We'll see that. Yeah, correct. At A0, at A0 you will get the serial output, correct. See, you take a parallel data out here, right? You take a parallel out here, so this will be available at Q A3, A2, A1 and A0, and then you keep shifting the data towards the right. So at A0 if you will get the serial. Yeah, thanks Venkat. So you will get the serial output at A0. So this can be used to generate from a parallel to serial, right? Similarly, for serial to parallel also, you can serially pump in data either from left to right depending on which is the MSB of the incoming data. If somebody is transmitting MSB towards the end, in the first itself, then you have to use the shift left. If somebody is sending the MSB in the last, then you can use the serial input for shift right here, so that the last input which is coming will be available here, and then you can use the parallel outputs. You can take this inputs parallelly. Is it okay, all these concepts, how these shift registers work? Right, anybody is having any doubt in serial to parallel conversion and parallel to serial conversion?
Excuse me, sir.
Yeah, tell me.
So how will this give a parallel out? You told us how it will give a serial out from A0. If we keep pushing 3 other bits in, or 4 other bits in, it'll eventually the first 4 bits will pop out of A0. But what about a parallel output, sir?
Parallel output is you give serially in. Say it is a 4-bit data which is coming. Once the 4-bit data is available, okay, then you take A0, A1, A2, A3 in the next clock. You take it into some register and store that data, and then again you start in for 4 cycles. You take fresh input. Okay, whatever is available in the 5th cycle, you take it into one more register. Then you give 4 more cycles, get the data input like that. Is it okay?
Okay, so we'll actually have to collect it from those A0, A1, A2, A3 into A3. Another bus.
Yeah, into some other register or memory location, whatever it is. Right, so you have to S1, S2 clock. These have to be controlled accordingly.
Understood, sir.
Right. Okay. No, clock will be there. S1, S2, S3. Whenever that at the end of that 4 clock cycles, you'll have to capture that data, whatever is available in A0, A1, A2, A3, into some other register. In between, there will be some junk data. If the bits are overlapping, when you are taking serial in 3 cycles, the bits will be overlapping. That will be a junk data. So you have to synchronize it when to take that data output. Okay. So your clock, like when you're transmitting, many times when you're transmitting from place A to place B and all, say such digital data, it will be in serial in nature, right? If you are making some data from lab A to lab B, okay, there will be some modem here, some modem there, and there will be only 2 lines which will carry data, so it will be serial data. But both the clocks have to be perfectly synchronized, right? So in case I finish up with this my theory portion, stipulated theory portion, I will talk about Manchester coding and things like that, how these clocks are synchronized. Okay, if there is time, I guess I will have 3-4 classes extra because we are moving slightly at a good pace. So if in those extra classes I'll include such inputs also. Okay, is it okay? Okay, so that's all. Okay, I have left out this portion. Okay, now say where do we use these registers? This is one application of the register. Okay, again this is not part of the syllabus. I have just put this slide to see. We have data encryption, right? You have suppose a data which is coming here, and this is the data at the receiving station. Suppose we do an XOR here. Okay, XOR. If I XOR with 1 here, right, the data will be inverted, and I do again XOR here, you will recover back the data. Similarly, if I put a 0 here, the same data will be available here, and the same data will be available here. Now suppose instead of giving this a constant 1 or 0, I give some random zeros and 1s here, so this entire data will get corrupted, right? But if I give the same sequence here, this whatever random series I am giving here, if I give the same random series here, right, the data will be recovered. So unless and until somebody knows the random series which I am giving at this point and this point, nobody will be able to decrypt my ciphered data. Cipher means you are encrypting it. Is it okay? Is this part understood?
Yes, sir.
Okay. So if I have to jumble up my data, all that I have to generate some kind of random number, and my receiving end also should know that random number. If it is only, that is known as end-to-end encryption. So this chap and this chap will know the random. So if this random number, if somebody else tries, it is very difficult for somebody to generate the exact random series which I am generating. Only that code for generating that random series will be known only to the actual receiver whom I have intended to transmit the data. So that is why he will be only able to decrypt my data. Okay, is this clear? Only then I can move ahead. Is it clear to all of you? Can somebody say yes or no? Yeah, okay. Now the next thing is how to generate these random numbers. Okay, random number is random, and you can't do anything about it. So you have something known as pseudo-random numbers. They appear to be random for somebody who is seeing from the outside, but for the chap who has designed it, it is not actually a random number. So this is a register, right? This is a register where I have, this is 3-bit register, and I am taking the output from this register and this register, putting an XOR and giving back here, right? So say the initial number is 0001. So the next value, if you see this logic, it will be 100. This you can verify. I'll share the PDF. Then it will be 100. Then it will be, so you are given it. So what happens is, so the output, if I take the output only from Q, from 2, it will be 1 0 0 1 1 1 0. Again it will have again this series following it. So if you see, if somebody tries to find out what is this series, it will be very difficult for him to know what is this series, because it is 1 0 0 1 1 1 0 0. So it is kind of random numbers. Okay, so it will be very difficult for a third person. Even if he tries to find out, it will be very difficult for him to find out what is this series available here. Okay, so this is but for you, if the receiver unit knows that this is the initial number 001 001, and it's a 3-bit register. So these two information is critical for the at the receiver station. 1, what is the register size? 2, what is the initial data which is to be fed here at particular time. At the same time, at that place also you will have exactly the same circuit available, and the clocks have to be exactly synchronized, and the initial data is to be given. So this is a second example which is given here. If you are taking it from these 2 bits XOR data, it will generate some other kind of sequence. See, it is generating some other kind of series, right? It is not the same series which is being generated. So now you can by using different combinations, initial conditions, here I can do initial 001 instead of 001 010. It will generate one more series. So I can change the sequence by changing the codes out here, right? What is being initially fed, and also by changing what outputs I am taking here. right? So in these two ways I can generate a large number of sequential pseudo-random signals. So it will become very difficult for, if you see so many combinations, the one who is intercepting this data, he has to try out so many combinations only for an 3-bit register here itself. Is it clear? Is this aspect to all of you? Anybody has got a doubt how we are generating these kind of series? This is not part of your syllabus, okay? Neither is it's going to be asked in the exam, but just for your information I am sharing. Is it okay? Or let's keep this in part of exam also. There could be few multiple choices. It's pretty simple. So now tell me, anybody has got doubt? No? Okay. So let's move on. See, this is instead of a 3-bit register, now I am taking to generate a series. Okay, this is what 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16-bit register. Okay, now you see the type of combinations which I can give. I can give any initial pattern. I can give 2 to the power of 16 combinations, any of the combinations, and then I can take XOR of any combination. So you see how the pseudo-random signal, the pseudo-random the bits might repeat after say 1000 bits also. Okay, the series will, like here it is up to 1, 2, 3, 4, 5, 6, 7, 8. Okay, here it is after 7. Right? So here if you use these kind of combinations, the signal, the random values may repeat after a long period. Okay, even the length of the sequence will also depend from where you take the output and things like that. So it becomes fairly complex for any third party intruder to get the code. So once it's encrypted within 16-bit register like this, taking the input, so the encryptor has to know how many bits register you are using. First information this he has to add. Second, what is the actual data you are putting it here, okay, before doing the XOR, and then from what all points you are doing the XOR. So all this information is required, and this also can be dynamic, right? So it could change on an hourly basis or in a day-to-day basis. You can this data which is there and these combinations, if you do that, it will become next to impossible for anybody to encrypt to decrypt this data, right? I told you maybe. So this is how we do this, like what in the ancient times. Okay, that's the end of the class. Let me just discuss, share some experience. When I joined Air Force initially, what the first cryptographic messages and all, what was it like? You have a text, right? A, B, C, D, E, F, G, H, okay, whatever. So there used to be a book in which okay, for today 1st of August, instead of A we will write C, okay, instead of B we will write D, something like that. It was the very ancient technique, right? You write, we used to write like that, okay, and on a particular day, what is to be replaced for A, B, C, that used to be in one book, and that book was kept very secret, only with it was Caesar cipher. It used to be kept only, it used to be held very secret, and it used to be available only with Air Force stations, and so it was not shared with anybody. So we could transmit like that, but then that was very easy to decipher. Like when you write messages, okay, there'll be some like to, for, so there'll be a few words which will keep repeating, okay, to, for, and something. Although there is an instruction key not to use such a to, for, a in those texts, but generally people tend to forget those instructions at various levels, and they'll use these words, okay, to, for, and all. So when you get those words, then we used to catch those words and then try to decrypt from there. Okay, T means this, O means that. So that way we used to manually. So even in Kargil war, I was in a kind of raw kind of organization where I was collecting few data and trying to decipher these things and all. So from ships and all, through Morse code, they used to send text messages from place A to place B. Most of the Chinese ships which were sailing there, they were covertly giving information. In fact, many of the people won't know that even Laden's position, actual position, was detected by the Indian agencies, which we gave it to the US, right? And so we gave some input. They might have cross verified it, but even through these messages only encrypted. Now that was age old when I say this ABC. Now that is all digital. So for digital, we do have lot of mathematics scientists who are there, who are working since ages on cipher systems. They have very, very complex systems. So whenever we intercept such data, it becomes difficult for an untrained person to decode it. So we used to send all this data to this one cell we had, where this old mathematician scientist used to sit there and try to decode this information. So we have lot of I was heading one unit which had lot of sophisticated electronic equipments to capture the data which is being transmitted. So we used to capture the data. Obviously the aircraft's transmission between each other in the voice band, VUHF band, they used to talk to each other. So that data though was in a plane. They used to talk in Urdu or Bangladeshis in so that too directly we used to intercept and make sense out of it if we can get some useful information. But otherwise whatever data was being transmitted, that was beyond us. It was encrypted with all these digital techniques. So at unit level it was just impossible to decode that. So we used to send that data to these mathematicians, and I believe there are some techniques even to crack this, sophisticated techniques to crack this. But those algorithms, when they run, it takes days together. Once you give it and they run in it in a system, it will take 1 or 2 days to give you some output. So those things are there. So it's an interesting field for those who are in computer science. Okay, so that's all for today. So now